In the last video, I gave you sort of the definition of continuities, saying if we take some function f of x, and I guess the intuitive definition of continuity is that I should be able to draw that function on the interval that's defined. And if you remember from the last video, we talked about the function the natural log of x, which is only defined from for numbers larger than 0. But if we took some function f of x and we were going to draw that function on the interval for which it's defined, we should be able to do that without lifting the pencil up off of the paper. We should be able to trace it without lifting the pen up. And then we talked about how that meant that each previous point was approaching. If we took any point, it would mean that any point on the line was being approached to by the points immediately before it and also the points immediately after it. And we saw that that was really what I guess the definition of continuity was, that if we took the limit as f of x approached any value c on the interval for which the function is defined. So if f of x is defined for all real numbers from minus infinity to positive infinity, then we could put any real number into c. And if we check for any number on the interval for which x is defined, and saw that number was going to be equal, that limit was going to be equal to some number, and we'll just call it L. And then we did the same thing for the limit as our function, as x approached that same value from the positive side. And if those two were equal, we saw back in the limit videos that if we approach the same number from the negative side and the positive side, then that means that our overall limit exists, that the limit as x approaches that value c without any condition. So this is like saying as x approaches some value c from either direction on the function f of x, then if this condition is true where these two limits are equal, then that means that this limit exists and it is also equal to what these two were equal to. So we called it L. So all these three things are going to be equal to L. And then we said for a continuous function, there was one more condition that we had to meet. And that condition was that the value of the function defined at c, so for any value c that we choose along this line, the value of the function at that point c has to also be equal to L. So all of these things have to be equal. And when all of these things are equal for every point c on the interval that a function is defined on, that is when we have a completely continuous function. And that was the definition of continuity. Now, what we're going to really be looking at, especially when we do these limit problems, and what's really going to be interesting about the limit problems, is when we start looking at discontinuities, and when we start looking at functions that aren't always going to be continuous, and trying to figure out, well, where aren't they continuous, and what do they look like when they're not continuous? So what we're going to talk about in this video is we're going to take a look at different functions and what they're going to look like when they are not continuous. So I'm going to go down here. And so these are the different types of discontinuities that you're going to see. There are three types of discontinuities. So I'll write that down. Three types of discontinuities. Sorry. Okay, so three types of discontinuities. And the first kind we're going to talk about is the infinite. So, infinite discontinuity. And the examples I want you to think about, and maybe I'll draw two different examples. Actually, you know what? I'm only going to draw one example here right now. The example that I want you to think about is the function. We're going to choose our function f of x is going to be equal to 1 over x squared. Now I want you to think about what this function looks like. And you can think about it as saying if we get really small numbers in here, if we get really small numbers and we square them, or as we get really close to zero, or first off, we know that we've got a discontinuity. The first thing I guess I want to say is that we know that we have a discontinuity here because we know that f of 0 is undefined. We know that f of 0 is undefined because if we plug 0 into this function, we get 1 over 0 squared, and that's just 1 over 0. And dividing by 0 is undefined. We don't have a way of defining that function. So we know that we must have some type of discontinuity here because we've found a value, like we talked about in the last video. In order for us to have a continuous function, we have to be able to do this process for any value c, along the interval that f is defined. So right here with this example of 1 over x squared, we've found our value c. We've found this value c where we can't do that process, where we can't say that our function is defined. We can't do this part of the process where we can say that f of c is equal to some value. F of c is equal to some limit L because the value of the function at that point c is undefined. So now I want you to think about what this function actually looks like. And what this function actually looks like, and this is a good function to just know off the top of your head what it's going to look like. And what it's going to do as we choose numbers that are really close to 0. And you can think about if we choose really small numbers that we're going to put in here for x, and then we square them, we're going to be dividing by really small numbers in there. So we're going to get, if you divide 1 by a really small number, you get a really big number. Or if you put larger numbers into this function, you're going to be dividing by larger numbers, and the value of your function is going to be a really small number. So what your function is going to look like, and remember it's going to go through the point 1, 1, because 1 over 1 squared is going to be 1. But this is what the first quadrant is going to look like of your function, and it's going to asymptote at our y-axis. It's just going to always be getting infinitely closer to the y-axis but never actually touch the y-axis. And the same thing is going to happen to our x-axis. As x grows, our function is going to get really close to that axis as we keep going to infinity. So that's what the positive side is going to look like. And now what's the negative side of our function going to look like over here? Because even if we're putting negative values in for x, we're going to be squaring it, so we're going to get a positive value out. And really the negative side of our function is going to look pretty much just like a mirror image of the positive side. We're going to have our function asymptote with the x-axis as we choose more and more negative as x goes to negative infinity over here. And as we get closer and closer to 0, so that's the point 0, 0, that's the point at x is equal to 0. And as we choose values that are really close to 0 but never equaling 0, we're going to again asymptote with our y-axis. We're going to get values that are closer and closer to our y-axis, but we're never going to get a point. Let me do this. We're never going to get a point here where I could be drawing my function here and then go like that and go back over the function, where fitting with my intuitive definition of continuity, I would be able to draw that without lifting my pen up. There's no real way to do that. If I was going to draw this function, I'm always going to have to draw it to some extent, it asymptotes, and then I'm going to have to start again. So fitting with our intuitive definition, this is a discontinuity. I can't draw it without lifting my pencil off of the paper. Similarly, if we were going to take the limit of this function from the negative side and the limit from the positive side, and I guess actually, you know what, that might be something for. Actually, I'll touch on it right here and maybe clarify it in the next video. But if we took the limit, let me do that right now. If we took the limit as 1 over x squared, of 1 over x squared, as x got really close to 0 from the negative side, then this is going to be equal to, well, and this is actually might be the first time that we're going to see limits defined this way. What does 1 over x squared approach as we choose values approaching from the negative side? So as we approach in this direction, what does the function get closer and closer to from this direction? And hopefully you can see that it doesn't approach a finite number, that this is actually going to approach positive infinity. And then, so hopefully you can see that. And I know this is the first time we're going to define a limit of something as being equal to infinity. And so far in the playlist, we've seen these limits defined as sort of finite numbers. So anyway, that's the limit as x approaches from the negative side. How about now let's do the limit as x approaches from the positive side of 1 over x squared. And hopefully you can see we're just approaching from that direction, and we're getting closer and closer to the y-axis, but we're never going to actually cross the y-axis. We're just always, as we get closer and closer to 0 here, our function is just always going to keep getting bigger and bigger and bigger. So here we're also going to have our function being equal to infinity, or our limit going, I shouldn't say, you never really equal infinity. You should say that the limit goes to infinity as x goes to 0, as x approaches 0. Because one of the, and this might be a good time to say here, never treat infinity like it's any type of finite number. You know, maybe I'll talk more about that in a future video. But I don't want you to think about this, oh, well, limit as at 1 over x squared as we approach from the negative side and the positive side, well, they're both going to be equal to infinity. You might be tempted to say, can we just plug 0 into this function and then say, well, that's equal to infinity? And I want to make it very clear that you can't do that. That if we were going to take 1 over, I don't even want to write it down as 1 over 0 squared. If I was going to just take f of 0, and don't write this down, but if you were going to write 1 over 0 squared, that is undefined. That is undefined. And undefined is not the same as infinity. So we don't have our point of continuity. We have a discontinuity here. Even I want to erase that. It's making me uncomfortable right now writing 1 over 0 squared on my paper. So if we were just going to say f of 0, that is going to be undefined. That is going to be undefined here. And undefined is not the same thing as infinity. So we are going to have a point of discontinuity here. So anyway, hopefully that makes sense to you. I'm really out of time on this video. So I'm actually going to end it here. That was the first type of discontinuity. And remember, I said that there are 3 types. Do it in a better color. There are 3 types of discontinuities, and that was the first one. That was our infinite discontinuity. So in the next video, sorry, I know I keep putting off these limit examples. In the next video, I'm going to show you the other 2 types of discontinuities. So anyway, thanks for watching, and I'll see you in the next video.